cannot scan a part and then remove it again. Here what we did, we started by CAD modeling, whereby we can design what we want to do. Here this is the mask, and this is the place which is not masked. And then the same we had to do like a reverse of it, whereby we have to consider the machining. AGM is supposed to have also the program which it will use to remove the material to each specific place. So it will be a kind of opposite design. And again, we had to go to do serializing so that we can work layer by layer. So our algorithm was understanding the two colors. It means it is understanding the black and the white. So the place with the white color, it is where it will put the mask, and the place with the black color, it is where there is no mask. And then we had, because we have to go layer by layer, we have to start by, if I go a little bit back, if we made the layer by layer, we had to go start by a small portion, another portion, until we will go to the end. And then something else we had to check is to check the toolpath, if it will give us the toolpath we want, because we have to have hatching distance. Because if we don't have hatching distance, it depends on the beam we are having. We have to understand it is necessary to set the hatching distance. If it is 200 micro, you use 100 micro or 300 micro. We have to check first of all. And again, after we took those parts I was showing here, we have to make sure that we will put all together so that they can be in the same program, which we simulated after putting all the data together. Because if we generate the code, usually it is generating for each part. So we had to make sure that we can put it together and then we can make the whole of it. Because if it will scan the whole of it until it will finish it. Then what we did for fabrication of the mask, here I want to show our setup. We have to use UV source, and then we have to have our optical system, and then we have to cure our SU8. It will be the workpiece. It will be soaked inside the SU8. This is what I'm trying to show, how the workpiece can look like if it is inside the SU8. But before we go to scan, we had to understand what is the wavelength we need to scan our SU8. Because the developer of SU8 has to analyze and show SU8 can be scanned very well if the wavelength is in this range from 400. Then we measured ours, we found it was around 600. So we concluded here that this system, it will scan, it will make our mask. And then we measured the beam size, because any size you want to make, you have to know the size of the beam we are having. Then when we measured the beam, we found we have a minimum around 324 and 321. I'm talking about the horizontal. If you look at the beam in the horizontal direction or in the vertical direction, this is how we can see the shape of the beam. If you can remember from the first point where how laser is working, it was supposed to have this shape. If we don't have this shape, it means our beam may be wrong, because the beam near the optical lens, it was supposed to be big, and at the end, again, it has to be a little bit big. So if we look at the table, it is showing we start by, if we are near the optical lens, we can have, for example, 700 micro, but if we go again far at 27, we again have B. But if we are at 18, we can have a small b. Then this small is what we need in our work. But if somebody wants to make, for example, just a big beam, he doesn't need to have the small size. Then here we developed a technique, because we have a problem, as we said. In the beginning, we had to eliminate spin coating, we have to eliminate edge bend, and we had to eliminate soft bake. So for our case, we decided to dilute this SU8, but at a very specific dilution range, because if we don't dilute at a very specific, we can have a risk of having different results. And again, you had to do immersing. Then something else here we had to add, instead of doing post-bake, we have done hard bake. This is different because some people, they do hard bake as an option, but for us we have used this hard baking because we have changed the properties of our SU8. The material we worked on, we have tried to work on 2-dimension, we tried to work on the glass, we tried to work on carbide, we tried to work on steel ball. So here we are trying to compare with this golf ball to see how the size was. Then in the chemical we had, in our environment also we had to use chemicals. The chemicals here was having a purpose. We had to clean the substrate, we had to use the chemicals for dilution, we have to use chemicals also for developing and rinsing. Here something we had to do, we had to measure the beam exactly. Even if we measured by instrument and we find it 324, we had to understand what is the beam size exactly we are having. Then we measured, we found 385.3 micron. Then we had again to scan to make a mask to know exactly what is the size of the mask we are able to make, and what is the hardness of it, and what is the surface roughness of it. Because if we don't know the hardness of this mask and we don't know the surface roughness, we cannot use it for our work. Then here we fabricated a mask, and then we wanted to see if we can fabricate on a 3D or on 2-dimension. When we fabricated this mask, just we were in a preliminary experiment to see if we are able to fabricate a mask on glass, or we can fabricate a mask on tungsten carbide. Then later we went to abrasive jet machining again to see if in a preliminary experiment, if we can machine and put some letters on the top of the surface. When we found we can be able to put some letters on the top of the surface, we had again to go back there to start to do our experiment, our main experiment, and then design the non-mathematical shape and mathematical shape. So this is some letters we made, and some shape we tried to make on the top of the surface. Here we made big because of matter of showing, because to take a picture of the mask, it was a very big problem to us because of the light reflecting. We are not able to take a small picture of a small mask. And here I tried to use camera to see if I can also take picture, but still the picture was not coming as clear. But what I wanted to see if it can show, it can make the hole, it can make the letter you want. Also it was making it. Then I had to go, after I made the mask, I had to analyze the mask to see what is the parameters affecting this mask. Because if we fabricate a mask and we don't know which parameter are affecting the fabrication, it was difficult for somebody to repeat the same experiment and to know which parameter he can say. Then I started by using the 5 parameters like a dilution ratio, because I changed the property of the mask. And then I had to consider the power, I had to consider the scanning speed, I had to consider also the area factor. This area factor, I'm defining the beam size, compare the ratio of the beam size to the hatching line. If I am putting the line, the scan path, I have to make sure that if I am doing 200 or I am using 100. And again, here I have used hard baking to make the hard bake time. So later when I analyzed, I found the factor most influencing the parameters are the root and the area factor, because we changed our SU8 properties, and then we put secoperol on the top of it so that we have reduced the viscosity. So after reducing the viscosity, definitely it was supposed to affect our mask we are fabricating. Then, but even if I have seen it is affecting, I have to see the relationship between the parameters to see if only area factor is a good parameter to if we were fabricating. But I realized even other parameters like UV power, scanning speed, and hard baking, they are affecting. So if I look at the graph, it means it is not only area factor which is affecting the fabrication, all the parameters are affecting. Then I had to go to see how the probability, because if you are making analysis, you have to see if the data are well arranged. Then I had to check the p-value, If the p-value is less than 0.1, it means those data are not, it cannot give a good result. So my p-value was 0.15, so I said it can give result which can make sense. Then I went to analyze again the surface roughness, because in my work I need to know the hardness of my mask and the surface roughness of it. Because of, if you want to cut, here there is a physics in it. If you have the mask in a photoresist, if you want to cut by using abrasive gel, if you are cutting hard material and you are using, for example, normal incidence, you can cut the hard material, but you will cut a lot of material from the workpiece, but you will cut raw material from the photoresist. But if you increase the angle, you will cut the mask more than you are cutting the workpiece. That is the reason why here we are trying to analyze those two parameters. Again, when I was looking, even if the scanning speed is more influential, I had to compare with other parameters, and I realized also all those four parameters, no one we are supposed to neglect. So it means if you look at the dilution factor and you look at the scanning speed, they don't have, if you look at the thickness means, you cannot see the big difference. So if I am making analysis, I had to keep considering those my 5 parameters. Then I had again to check my probability to see how the data are arranged for surface roughness. I found my p-value was 0.416. So this is more than 0.01. So again, the data was well arranged, so it can make, the result can make sense. Then I said if I finish to know the most influential parameters, I had to make sure that I can give like an empirical formula whereby somebody can use to fabricate. If he will come again to use the same experiment, he was supposed to have the parameters, and then he can do the relationship between the input and output. But here I had to set the levels, the minimum you are supposed to be and the maximum you are supposed to be, because if we don't have any range we are using and we go to our system, we have a high risk of not having a mask. For example, I was using a power before of less than 20 micro. It was very hard for me to fabricate a mask. But when I changed my power to around 150, it has improved a lot in fabrication of the photoresist mask. Then I developed, that is the reason why I developed this system whereby if we want to UV energy, this is microjoule per unit length, because if you have the power in the scanning speed, they have relationship between power and the scanning speed, because the scanning speed will dictate the power it will be on the specific point. If we increase the scanning speed, it means you will modify also the power going to the surface. Again, I had to consider the beam size and again the ratio I am using for dilution, because here the dilution for SU8, it was important, because if I don't dilute SU8, I cannot use it. Again, I had to consider the hard baking time. Here, when I analyzed, I was considering, because I have used the box bacon design of experiment, he's dictating if you have 3 parameters, you can use 15 experiment, and then you do this kind of combination. And then if you do this combination, it will tell us how we can analyze those results we are having. In the preliminary, we managed to get the surface roughness and this kind of hardness. Then we had to analyze by using an ANOVA table to see how the hardness, but we had to put the risk level at 0.05. That is, this risk level is also, this is what is dictating for the result we are getting, because if we have to, we can set risk level to 0.1 or we can use to 0.05. But the important is, we have to check if the p-value will be less than 0.05, it means that parameter which is giving that p-value, it has to be considered in the model. It means this is a very important parameter. When we are looking at this hardness, we realized here we gave it the names like A, B, C, D, because we are using, if we go a little bit back, A is energy, B is focal ratio, and the C is hard baking. Then we had to see how we can do this combination to check what is the p-value and what is the relationship it will have. This is b times a, beta b squared, this a squared, this b times c. So that is how we are trying to see that relationship. Then we had to check the main effect, the main effect plot to see if those parameters they are having a relationship. If they don't have, if they have interaction in between, it means those parameters no one is supposed to be neglected because one is having effect on another. Then we had to check to see how the results are distributed, considering fitted value to actual values. Then at the end we developed a model considering those parameters it is giving us. Then we had to take those parameters. The way you have those parameters multiplied is the way we are making a formula out of it. Then we went to surface roughness. We did the same. We had to analyze from the beginning, and then we had to check the p-value because the p-value is very important if we want to see the relationship between the input and output. So here no parameter we are supposed to neglect. That is the reason why I put in the color. All of the values are less than 0.05. Then we had to see, again for surface roughness, if those parameters are having a relationship. Then we realized they are having a relationship, so we don't have to neglect any parameter. Then you have to see how the data are distributed. If data are not distributed near this line, it means your data cannot give the good result you want. Then I generated a model out of those results. I realized if you want to get this kind of hardness, you have to use, if you use those parameters A, B, C, D, and then you use this multiplication, you can have a specific hardness according to the data you are having. Then I had to optimize the process to see what is the optimal condition we can fabricate mask with which parameters. Then I had to set the minimum hardness of the mask I need and the surface I want. Then I realized we can use those parameters. For example, if we set this condition, we are supposed to have a hardness which is around the 6 HV. That is, we are using microvicas to measure the hardness. And then the surface roughness, you have to use a non-contact method. So if we predict with our empirical model, we can have those data. So, but if you get those data with empirical model, you have to go to do experiment again to see if what you are predicting, it can make sense. This is one of the, for example, one of the optimal condition I was taking. If I am taking energy of 11, and then I'm using focal ratio of 4.89, and I'm using baking time of 8 minutes, I was supposed to have this hardness and this surface roughness. Then I sent my data outside to measure the hardness and the surface roughness. Then I realized when I wanted the 6 HV, I got 22. And then, for example, for this 7, the experiment I was showing now, it was giving 25, and this surface roughness. This hardness and this surface roughness, when Professor Ko and Agungu did their experiment by using photolithography in 2007, they published a paper showing they managed to get 25 hardness. But they used another option by using photolithography and doing spin coating. But I saw only one result from that paper. They didn't show like the whole process, many data. But when I got 25, I said because they got it when they did using this different option, and I get it with my option, I said this hardness can make sense. Then I was considering what I was predicting and what I have received. I was predicting from this graph, and then I was received from this. It means the hardness I predicted, what I got was bigger than what I was predicting. Then I was again go to prediction for surface roughness. Then I realized the surface roughness, what I was predicting, it was near to what I have seen, and the minimum was 1.4.